So next, let's talk about permutations, which in my opinion is a bit more complicated than combinations or subsets, but maybe for you it will actually be easier, who knows. Basically, we could be given some list of numbers. Let's assume that the numbers are distinct for simplicity, and we want to return all possible distinct permutations of nums. So first of all, what is a permutation? Because it's different than a combination. It's kind of the idea, instead of for each number, whether we include it or not, right? Every, possible subset of these numbers, we are including every single one. Like that's going to be a permutation of nums. We include every single one of these, but we possibly rearrange the order of these. So we have 4 spots, we know that, but we want to rearrange the order. So how many possible permutations could we create of these? Well, for the first position, we can possibly choose any single one of these. So we have 4 possible values we can put in the first position. But after we've put something here, we can't reuse the value. So whether we put a 1 here or we put a 2 here, we can't reuse that value. Then we would just have 3 choices left for the second value. So we'd have 3 choices here. After we made the first 2 choices, we'd have 2 choices left. After we make those, we just have 1 choice left. So basically 4 times 3 times 2 times 1. Another way of putting that is 4 factorial. So we say that the possible number of permutations we can create with an array of arbitrary size is going to be n factorial. So we know this is how many possibilities are going to be in our result of permutations. So to create all permutations using backtracking is what I'm going to show you first, but actually you can also do this using an iterative solution as well, which I'll show you in a bit. But there's actually multiple ways of going about this, even like thinking about it logically with a decision tree. So one way to think about it logically is that for each layer, we're going to be choosing a position. So for the first layer here of our decision tree, we're going to be choosing the first position. For the first position, we can have either 1, 2, 3, or 4. And then for the second layer below that, we have 3 choices, but this is going for the second position. So for example, for 1, we have every value other than 1. So we could do 2, 3, 4. For 2, we could do the other 3 values that are not 2. We can do 1, 3, 4. Notice how we do kind of have a duplicate here, 1, 2 and 2, 1, but that's okay because for a permutation, 1, 2 is different than 2, 1. The order matters. Since these are in a different order than this, these are different permutations. So this is actually fine. And we can continue doing this decision tree like this. Like here we'd have 3, 4, here we'd have 4, and here we'd have 3, and then this would be 1 permutation, a second permutation, and we could expand the tree just like that. We have n layers here, and children. Here we have n minus 1, and then we keep going like that until we get down to 1. So multiplying all these out will give us a time complexity of n factorial. That's where, this comes from. And this is a perfectly valid way to think about it, but coding it up this way is a little bit more annoying in my opinion, because you have to kind of remove from this array to expand upon the children paths. So another way to do it is similarly for the first step, we'd have, 1, 2, 3, 4. But for each of the paths, we expand upon it differently. Like at this point, we have an array of 1. What we do for this path is every number that comes after 1, so here we have 2, 3, and 4, we're going to insert each of these values in every possible position we can. So in this case, this 2 can either be inserted before the 1 or after the 1. So we're going to do those paths for this guy. We'd have 1, 2, and we'd have 2, 1. We do the same thing for 3 and 4. So we'd have 1, 3 and 3, 1. And we'd do the same thing with 4. So we'd have 1, 4 and 4, 1. And then for each of these, we expand upon it similarly. We basically break it into a subproblem where we start at the first position. So we have an I pointer and we start at the first position. That's pretty typical for these backtracking problems. But we say generate all possible permutations with these 3 numbers, and then I'll include 1 in that. So basically we pass I plus 1, so we end up here. But for here, we do the same thing. To generate all possible permutations with these 3, let's first generate all possible permutations with these 2. So we do the same thing, and then here we'll do the same thing. Instead of generating all permutations with these 2, first generate all permutations with this. Now that's going to be the base case. So you can kind of see how this solution in a way lends itself to iteration, which is what I'm going to show you eventually. But in terms of recursion, you can kind of think about it. We, made 4 kind of recursive calls, and eventually we got to the point where we had just a single 4 that was returned to us. So I'll just kind of put a 4. So that was the permutations we could create with just the single value. Now to that 4 itself, we can either add the 3 at the beginning of the 4 or add the 3 at the end of the 4, because now we're trying to create all permutations with these 2 numbers. So that's what we would do. Now we have this. This was returned up from the second, from this recursive call, basically up to the parent here. Now here we're trying to do all permutations with all 3 values, 2, 3, 4. So basically we have these 2 permutations. We're going to create a copy of this permutation, add a 2 at the beginning of it, which would give us this permutations, 2, 3, 4. And we're also going to try to add a 2 in the middle of it, which would give us this permutation, 3, 2, 4. And we're also going to add a 2 at the end of it, which would give us this permutation, 3, 4, 2. And we'd also, this is obviously going to start becoming a big list now, because we would do the same thing with this permutation. We'd add a 2 at the beginning of it, add a 2 in the middle of it, and add a 2 at the end of it. So that's going to give us 6 permutations here. And then for each of those 6 permutations, which each have 3 values in it, we're going to try inserting the 1 in every possible value. So the 1 is going to go at the beginning, in between these two, and at the end. So we'd have 6 permutations here, multiply those by 4, because 1 value can go in all 4 positions. So then we'd end up here with 24 permutations. So how many permutations is that? Well, that's equal to 4 factorial. So this is just a different way to think about it logically. The main reason I'm showing you this way is because it's easier to code, but you can also implement it the other way, where I kind of showed you we're actually branching with the decision tree. It's up to personal preference. But if I showed you the more complicated way to code it, then people would ask, hey, well, there's a simple way. Why didn't you show that? So I prefer to show you the simplest solution. So let's see how we could code this up. It's a bit different than the other backtracking approaches we've seen so far. So here's how we can compute the permutations recursively. The time complexity is going to be n factorial, because that's how many permutations we're going to have. Each permutation is going to be of size n, so n values in it. So that would be a time complexity of n times n factorial. But lastly, you saw the way we were generating these permutations. When we had a permutation, let's say of size 3, we had, for example, 2, 3, 4. Then for the 1, we want to insert it in every possible position. And then we'll have a resulting permutation of size 4. Now, to have built that permutation of size 4, it wasn't straightforward. It wasn't that we just added a 2, then added a 3 at the end of it, and then added a 4 at the end of it. As you can see, when we have this 1, we're inserting it at the beginning. To insert at the beginning of an array is not a O of 1 time operation, it's an O of n time operation. To insert that 1 in between these two, same thing, it's an O of n time operation. So to arbitrarily insert a value in any position of an array is O of n. So to build each array normally would take O of n if each insert was an O of 1 time operation. But if each insert is an n time operation and we're doing it for n values, then to build each array is actually n squared. So to build each array in the output is n squared. How many of those arrays do we have? N factorial. So this is the big O time complexity here. It's easier to analyze the big O time complexity for this problem, thinking about the math actually, like how statistically these are actually built and calculated, rather than looking at the recursive solution. It would be pretty complicated to get the time complexity from looking at this, in my opinion. Code-wise, you can see there's not a lot here. We have our permutation function where we're just passing in a list of numbers, but then our helper is going to actually calculate those permutations because we're going to be moving through the array. We're going to start at index 0 of our array. That's what this I pointer is for. By the time we reach the end of the array, we actually do need to start with a base case. We could have actually made our base case here be when I is equal to length minus 1, in which case what we would return is a single permutation with the last value, kind of how I showed in the drawing explanation. We would have returned a 4, a list with just 4 inside it. And actually this list will be inside of another list here, but what we're actually doing here is we're just returning an empty list with an empty list. basically. And then what this will actually do, suppose this is returned from the value I, then it'll be returned back to the call where we're at I-1. So that would mean our I pointer was here, but then we popped back to this position where we're at the last value. And for that, what we would say is for every array in our return value in our list here, we're going to create a copy of this and then insert the 4 in every possible position. So what we're saying is here we recursively call our helper from, here we'd call the helper from this index and then to this index and this here and then here, and then we would get to the base case that I'm talking about here. So after we get that base case, then we're going to go through every permutation in the list of permutations. Here we just have a single one that's empty. And then we're going to go through every position in the length plus 1 here, because for an empty array, we have one position where we can insert it. For an array of size 1, we have 2 positions where we could insert it. We can insert at the beginning or we can insert at the end. For an array of size 2, we have 3 positions where we can insert at the beginning, middle, and end. That's the idea here. That's why we're doing length plus 1. And then we're creating a copy of that permutation. And then for that copy, we're taking our nums of I value and inserting it at every possible value. So this J is basically a pointer that's going to iterate through every position in that permutation. For this simple base case, it's just a single one here, and we just have 4. We're going to insert 4 at one position. So then from here, the return value, we basically have our result of permutations. We initially had permutations. This was the return value from our recursive call. And then we have the result permutations that we're building, which would, from this, just basically be this. So just a 4 inside it. And then from here, we would return, our I pointer would be back at this 3. And then for this, what we would do is create a copy of this, insert 3 in every position. So one copy would be 3, 4. And then another copy would be 4, 3. So that's why we're creating a copy of these, because we want, distinct lists for the possible permutations. And then this would be our result permutations, which we would return here. And then we'd kind of do the same thing where we're now going to be, our I pointer is going to be at 2. For each of these, we create a copy of it and then insert 2 in every possible position. So 2, 3, 4. You probably get the idea here. It's going to be a lot to write out, so I'm not going to write out all of these, but the 2 could also go in the middle. It could also go at the end. So that's this inner loop. For each position that we can put the 2 in, we're going to create a copy of this, insert that 2 there, and then take that and add it to our result. And after we do that for this, we're going to do it for the second permutation. We're going to do it for every permutation in this list. So we would do the same thing for this guy, and then we would return. And that's pretty much the entire idea behind this solution. So this is definitely tricky. The way I'm showing you is kind of the clever way to do it in terms of code, because it ends up reducing the code that we write. But you could do this a different way, where the nums that you're passing into each recursive call, you're actually removing from that. Like where initially you can see here, we start out with all 4 values. And then for each of those 4 values, we want to potentially make a decision. We want to do 1, 2, 3, or 4. Then for each of these children paths, for the 1, you would want every value to be available except for the 1. For 2, you would want every value here to be available except for the 2. So maybe recursively, you could pass in nums after removing 2. That's a different approach. It makes more sense visually, I think, but in terms of code, it would be a bit more complicated. But I encourage you to try writing that out if you want to practice things. But now let me show you how we can solve this same problem, basically translating this code into an iterative solution. Because you might be thinking the way kind of we're doing this, where we initially have just a list that's empty, and then we transform that into a list of just a single value, and then we transform that into larger permutations, and we keep going. It does kind of make sense that this could be done iteratively. So you can see here that the iterative code is actually even shorter, but that doesn't always mean it's more simple to come up with. By now, we definitely know that. So you can see we're starting with an initial empty list of permutations. Technically, we just have the empty permutation. That's not really a valid permutation in this context, but it's going to help us build our result. So we're going to go through every single number in nums. So first, we're going to build all permutations with just the first value, just because it's more simple. I mean, we could iterate through this in reverse order just to be consistent with the recursive solution, but there's no need to do that. We can also start at the beginning, do all permutations with the first value. then build all permutations with these two, then with these three, and then finally with all four values, and that's going to be our result. So what we here say is this is our next list of permutations. This is our original list, and next we're going to build the permutations with all one values, and then this is going to be our list of permutations, and then the next list of permutations we try to build is with two values and then three values. What you can see we're doing is after we build the next list of permutations, we're assigning that to our regular list of permutations, and then we start the cycle over again until we've built it with all of these values, and then we would return that. But first, just starting with the first value here, we're going to go through our list of existing permutations, which is just an empty permutation, and insert the n value here to every possible position, so every I index in this guy, but there's only one just, at the 0th position. So that's what we would do. We would have our permutation of just 1, and then we want to build all permutations with the second value included. So we would go through all our list of existing permutations. We just have 1 here, and then we would try to insert n in every possible I position of that permutation. So we try to do 2, 1, inserting it at index 0, and then we would try to insert it at index 1, which would be after the 1. So we'd put 2 over here, and then these are basically the permutation copies that we're building. And when we after we insert a value into it, then we add it to our list of next permutations. As I kind of drew over here, this is our list of next permutations, and then this is what our perms would be assigned to, and this would basically no longer be in memory. And then we'd have our next list of permutations, which would be an empty array where we would take these, create copies of them, insert in this case 3, our I pointer would be over here, and build that next list of permutations, keep the cycle going, and then eventually return the result. So this is, again, not super crazy in terms of code. The time complexity is pretty hard to analyze from just looking at the code, but conceptually, we know mathematically this is what's actually going on here. Each time we insert, this is where that n time operation is coming from. Each permutation is going to be of size n, so that's n squared. The number of permutations we're going to have in our result is always going to be n factorial. That's just kind of mathematical. So that's going to be the overall time complexity here. So this might have blown your brain. I'm not sure. Who knew you could take recursive solutions and also write them iteratively? So maybe this doesn't even count as backtracking. I think it sort of still does, but it's definitely a different way to do it. But there are different ways of calculating permutations. There's actually several different ways you can write this code. I encourage you to try writing it a different way if you'd like, if maybe this way doesn't make a ton of sense to you. I think this probably is code-wise the easiest way to do it though.